Hello and welcome. This is Chapter 2, Section 5 on free fall. This is our first application of the equations of constant acceleration to a physical situation that we all observe, and that's, of course, falling objects to the ground. So these pictures are pretty striking, and if you've ever seen videos about this where they put feathers and kind of massive balls or objects or apples into a vacuum chamber and suck out most of the air, then the feather and the apple drop at the same rate. Why is this? Well, that's not really the question that we want to answer now. What we want to do is just apply this and understand the motion of it. We'll get to the why when we do forces. Okay. So the motion of an object moving under gravity and no other forces is called free fall. Of course, we will define forces in more detail in Chapter 5. Chapter 5 has a complete catalog of all the lots of different forces we will encounter. But this is basically ignoring air resistance. And another thing to consider is that these objects are not falling from such a large altitude. Like, for instance, if you drop a rock from rest at the height of a GPS satellite, its acceleration is not going to be constant, even though there's very minimal air resistance and gravity is the only force. So these words, you got to be careful that you make simplifying assumptions. Right. So evidently, objects, regardless of their mass, again, another topic for Chapter 5, they have the exact same acceleration. So a rock and a feather have the same acceleration, an apple and a banana. Any two objects, no matter how big or how small, a tiny raisin and a huge bowling ball, they will hit the ground at the same time. And this is fascinating. We'll learn why that is in later chapters. But for now, let's quote the value that we will be using for the free fall acceleration. It's this value right here. Let's make sure we understand what this number means. So this picture or this equation down here is a vector equation for free fall. This is the vector equation for it. So vector equations have to have a magnitude and direction. So we're going to say that the magnitude of this free fall acceleration experimentally is 9.80 meters per second squared. And of course, the direction is always vertically downward, even if you're throwing a football or throwing a baseball or basketball horizontally, it's still accelerating downward. And a couple comments on this 9.80. This actually changes with latitude. It's actually a lot more than 9.80 near the poles, and it's actually slightly smaller than 9.80 near the equators. And that's because of an effect that has to do with the object's rotation, or the Earth's rotation, actually. So 9.80 can be more or less the kind of latitude averaged value over most of the United States. Like closer to the equator, maybe Texas, maybe Florida, maybe we're looking at like a 9.79. Upwards in the Pacific Northwest or the upper Northeast, maybe we're looking at a 9.81. So how do we explain this mathematically? Well, we use our kinematic equations of constant acceleration, except now we replace the acceleration with g. And an important thing is that there is, so in this equation right here, we've got acceleration in the y direction is free fall acceleration minus g. So g is a positive quantity. It's not gravity, even though it sounds like gravity, because it's a g. It is the free fall constant. That's what I will always refer to it as, the free fall constant. And why is it positive? Well, because it's the magnitude. Okay, the vectors have a magnitude, a non-negative magnitude, and a direction. In one dimension, it can be positive or negative, but the magnitude is always positive. So that's why that's what we mean when we say that g is a positive quantity. So we've got a vector, or we got a motion diagram of the thing, and we have a graph as well. This looks accident. This looks like a velocity versus time graph for an object that's dropped from rest. What would the acceleration graph look like? Well, the acceleration graph would just be a straight horizontal straight line at minus 9.80. And then what about the position versus time graph? Well, if the velocity is linear, then the position has to be quadratic. And so it would be a quadratically increasing downward concave parabola that starts at rest with a zero slope and then increases further down. Okay, so this is an example. Oftentimes these free fall problems will have like a leap or a jump or a throw, and then how high does it go? Those are the types of problems, those type of two-step problems that these gravity examples like to do. So once again, this is something that I would recommend you go through on your own. Try to solve the problem without the help of the example. This is how you learn physics, just by doing problems. Unfortunately, you got a good one right here. But we can certainly look at in the slides though, we can certainly look at the pictorial representations. So we've got a period of time where we're accelerating upward. This is the jump. Okay, we start at rest, and then we have a very large acceleration. And then once your feet leave the ground, now you're in free fall. Or once the feet for the kangaroo leave the ground, now we're in free fall. So once our feet leave the ground, evidently we instantaneously switch from a positive upward acceleration to now a downward acceleration of g, minus g. And right, and again, you see this little stick squiggly circle figure that they drew. You don't need anything too complicated. Sometimes I just draw a box. And then, writing, of course, down what we know. We want to know how high up we go, given that we know the accelerations of both of them. 35 meters per second squared at the start. That's pretty fair. A little trick is that if you know the accelerations, then you can how high they go. You can find the ratio of the two displacements. That's kind of an advanced trick, though. So, good example of free fall. I would recommend you try to look at the graphs of, say, throwing a ball into the air. What would the graph of this thing look like? Does it show it? No, it doesn't. So the graphs of this jump for this kangaroo is actually pretty interesting. Okay, so now we have the graphs overlaid on here. I'm going to really quickly sketch them out. The book looks like it doesn't do this, but I think it's very helpful in this example. So when you draw these graphs, I would certainly start off with the acceleration at the bottom, and then the velocity in the middle, and then the position at the top. So what's the acceleration? Well, the first part of the jump is a very large 35 meter per second squared value. And then after the feet leave the ground, it jumps down immediately to negative 9.8. So this right here is negative 9.8 meters per second. And this right here is 35 meters per second. So we have an acceleration that starts off very large and then instantaneously jumps down to a negative acceleration. And what are the implications for the velocity versus time graph? Well, how do you go from acceleration to velocity? Look at the definition. If you have, so kind of draw them stacked on top of one another, that way their time axes align. So what does the velocity versus time graph look like for that first instant? It is just a sharp straight line upward. It's supposed to be a straight line upward. And then after we decrease to minus 9.8, then it is a shallower descent, a little shallower. I'm going to try and get this right. And it'll just kind of continue. And this point right here is called the turning point. The turning point is where the turning point is where the the velocity versus time graph crosses the t-axis. So we change direction. And then finally, what is the position versus time graph look like? The one at the top. It's two different parabolas, but there's one important thing I want to mention about these parabolas, and that is one is concave up. This first one is a sharp concave up parabola. I'll draw that a little bit better. It's a sharp concave up parabola, but that is followed by a concave down parabola. So we start off like this, and then we have a parabola like this. Okay, so these are two different parabolas. This is not like a cubic function. This is two different parabolas that are stitched together at that point where the state of the acceleration changes. The slope of the position versus time graph at that spot is the value of the velocity at that point. And when the slope is 0, at this top spot, the slope is 0, that corresponds to the turning point. So the turning point, when the velocity is 0, is a maximum on the position versus time graph for this kangaroo. Of course, the problem doesn't really go on and say, because eventually you'll fall down and then he'll reach the ground again. But yeah, we have two parabolas are stitched together. And so when you're combining uniform motion with constant acceleration, what have you got? Acceleration is allowed to be discontinuous. Okay, it's either 0 or it's a constant value. It's not going to jump up to one of them. And that's going to mean that acceleration is defined or is required to be piecewise continuous. Then the velocity graph is required to be continuous, but not necessarily differentiable, because that kink where the state of the acceleration changes is not differentiable at that point. And yet the position versus time graph is required to be continuous. It's also required to be differentiable, but it's not required to be twice differentiable. And the points where it's not twice differentiable are where there are kinks in the velocity graph, discontinuities in the acceleration graph. This is a good example to go through and make sure you understand the graphs of these position, velocity, and acceleration versus time graphs for particles moving with kinematic or constant acceleration. So I thought that was a good opportunity. That's it for this section. We're going to continue with a second application of constant acceleration in the next video. So thanks for your time. We'll see you back here in the next one. Take care.